Welcome to Astronomy Modeling Sneak Peek.
Welcome, welcome. Please feel free to turn on your video. We love to see faces. I mean, and we don't care whether your hair is combed. No,
Yeah, I
honestly,
didn't comb my hair. I just put a
mine
hat
is
on.
barely combed, and Dan is hiding his altogether because he's in a very cold room. Hi, Lydia. Hi, Kathy.
Morning.
Hi, Aaron. Hi, Sumangala.
Hello.
Hi, everyone.
And then that one hiding behind the AMTA sticker is Sue Ray, our Wizard of Oz, the person behind the curtain that makes it all happen.
Hi, Sue. Thanks, Sue.
And
Hi, everybody.
Johanna, greetings. Welcome to the sneak peek of astronomy modeling instruction. Okay,
And
it's
if your
okay.
camera's not working, thanks for letting us know.
It's fine. It's fine. You know, we thrive on faces, but we understand sometimes people's technology has limitations. I'm Colleen McGowan, and I am one of the co-developers of astronomy modeling with Dan Peluso, and I'm also AMTA Senior Fellow. I used to be the executive officer, but then I handed off to someone else so that I could spend time doing more interesting things like developing new workshops and curriculum resources and getting grants and doing research.
Yeah. And I'm Dan Peluso. I recently finished my PhD in astrophysics, focusing on exoplanets, planets around other stars. And it also had an education component where I worked with Colleen, who was one of my PhD supervisors, on further developing astronomy modeling and a whole citizen science initiative using these small telescopes called unistellar telescopes to allow teachers and students to collect data on astronomical objects and to learn by doing and collect data, which is what we're all about with modeling. So we'll might have a chance to talk a little bit more about some of that stuff later. I currently work for the Legacy Survey of Space and Time Discovery Alliance, which is a new and astronomical project that is going to be starting in the next year or so. It will be a household name once they have the first light for the telescope. So if you haven't heard of it yet, the Rubin Observatory, you probably will in about a year. And if we have time, we'll chat more about it later.
But there's already a good education component associated with the Vera Rubin Observatory that has come online, and we've got AMTA has a relationship, you know, because Dan and I have a relationship. We have a relationship with them. We're doing a series of webinars on you know, classroom astronomy. So, well, welcome those of you that just arrived. I'm Colleen, this is Dan. We just introduced ourselves, but you know, the main event isn't who we are, it's what we've got for you today, which is astronomy modeling instruction.
Yeah, I'm curious, just real quick, do we have any new modelers? Anyone that's never taken a modeling webinar or workshop before? Is anybody new to what modeling is?
Okay, there's one.
Okay.
Okay, cool. You can use little buttons to raise your hand. So then we're going to assume that most people here in the room are at least glancingly familiar with modeling instruction, which is, oh, Anna, okay. Okay, Sumangala, am I saying your name right?
Yeah, that's correct, Colin. Thank you so much.
Okay. Are new to modeling. So modeling instruction is a method of teaching that is based on helping students build, refine, and apply the fundamental conceptual models.
Colleen, I'm going to put that slide up that has some cool pictures while you talk about this, because I think it goes hand in hand with what you're saying.
Yeah. The fundamental conceptual models of some scientific disciplines. So in physics, fundamental models that we uncover are things like constant velocity, uniform acceleration, balanced force, unbalanced force, energy, momentum. What we're going to uncover for you today, just a little bit, is some of the fundamental models in astronomy and give you a taste of what doing this with students would look like. All right, I'm gonna let you take it away with the slides, Dan.
Sure. Yeah, and just to give you a little bit more historical context, modeling instruction began in the 90s around physics, like Colleen said, but only recently has been adapted or been used for astronomy. And I like to think of modeling as a way where students learn by doing. It's very data intensive, lots of data involved in it, and how we work with collecting data and understanding it to understand the natural world, do science like scientists do. And this is where teachers, we're no longer the sage on the stage, but we're the guide on the side. And it's a hard transition to make because we're taught with sages on the stage our entire lives, all the way through university. But I had struggled with this whenever I first started teaching. I adopted the sage on the stage model, and then when I learned about modeling, I started to do more guide on the side practices, and then spent some of my PhD trying to understand modeling and putting it into practice. And I could tell you it's a big changer in the classroom when you start adopting the guide on the side model. It's a big change in a positive way for you as an educator and for the students. So just a couple of quick things to add. There's been a lot of support for modeling instruction. There's a lot of peer-reviewed publications that have shown the effectiveness of this pedagogy in the classroom. In fact, Colleen and I have a paper that is currently, it was in peer review, and we're about to resubmit it about astronomy modeling, the only astronomy modeling paper that exists. That should be submitted soon. It's all my court, Colleen. So as soon as I'm done
Yeah,
things,
we'll get it done.
Yeah.
Publishing is slow work, one step at a time, right?
Yeah. But the point is, we do have a lot of great, we're educational scientists, so we like to collect data and understand if what we're doing works, and what we found is it does. And that's what we hear from our community too. And we've had over 20 years of National Science Foundation support. And in fact, some of you that might have been on a little earlier before the start of the workshop, Colleen and I were already brainstorming about new grants that we're going to look for to have even more National Science Foundation support in the future. And we offer these professional development webinars like you're on today, but also full graduate level credit workshops. And one of those that Colleen mentioned was the astronomy modeling instruction with exoplanets workshop, which starts in January. That's a full 15-week course where you can get graduate credit for it if you choose to. So this is a teaser of it today.
Yeah, and Dan and I have led this workshop twice before, and Dan and someone else led it last year. I was busy with something, but it inevitably produces an enthusiastic group of teacher astronomers. And in at least one case, Dan managed to hook one of them up with an EV scope, which is a very cool telescope that might be in one of those pictures down there.
Yeah, at the bottom right-hand corner of this picture, that you see these with this the silver telescope. That's a EV scope. It's a new type of digital smart telescope that is manufactured by a French company called Unistellar. And if you've ever used a backyard telescope before, they're very frustrating because you have to try to point at things, and it's hard to know where things are at. And it's using traditional like mirror and lens optics, so you can't use an exposure like you can on a camera to collect more light, which is something we're going to talk about today. So I don't want to get too much into that, but it allows you to get really beautiful images of the sky and also collect data. And students can actually be involved in publications. In fact, in the bottom right-hand corner, there's a little graph there, which is the evidence of an exoplanet, planet around another star. And that data was collected entirely by high school students using these telescopes and using modeling instruction as the pedagogy to help them understand what they're doing. So it's a really exciting way that we can change how we do science. and education together, like in one. And this came about, and I won't spend too much more time on this so we can get started. But this came about by, I have to just mention Dr. Carl Pennypacker, who had this idea in the 90s where he wanted to get people like teachers like you and students access to real telescopes and teach them the actual skills that an astronomer uses to do science research. So instead of just showing pictures and reading out of a book, it's like, let's actually do things like an astronomer actually does. But Carl never knew about the pedagogy that was, effective to, to implement this in the classroom in the best way. And then he found out about modeling instruction. It's like, well, let's do this with astronomy. And that's kind of how this all came about. And yeah, so it's about doing real astronomy and real science, and with the same modeling pedagogy that has worked for physics.
Has anyone here, let me ask, has anyone here ever heard of Global Hands-On Universe? If you've done some astronomy activities or attended other astronomy professional development, you may have heard of Global Hands-On Universe. That was Carl's project that he launched in the 90s, right around the same time that modeling instruction was launched by David Hessenis at Arizona State University. So these are two venerable old programs that are still reaching out to teachers and helping them, teach students to do science, not just to read about science.
Yeah, and the last I'll say on these slides, and I think I'll save the other slides for after we do activities with you, just because I don't want to give too much away at the beginning. But I just want to point out the picture in the middle with all the aliens. Those are my students. They are aliens. I had a joint research appointment with the SETI Institute, the Search for Extraterrestrial Intelligence, here in Mountain View, California. So I got to teach aliens, alien high students. But so the picture, this includes me with my students, and they're holding whiteboards. So in a modeling classroom, we in person, we use these whiteboards, and you can see how big they are. They're, what is it, like
24 by 32 inches.
Okay, 24 by 32 inches. Eventually I'll remember that, and I should know that.
Someday we'll learn what that is in centimeters, but not
yeah.
today.
So this is where they build their model and brainstorm on it. And it's really effective because when you're at a small group, of 3 to 4 students, everyone has a marker, everyone can get involved. And even that student that, might be not really doing anything, like just kind of, letting the other group members do the work. That doesn't happen. Anybody else does it. But even those students that aren't necessarily fully participating as we want them to, they still have a marker and they still might do something. They're still getting more involved than they would otherwise, right? And we find a lot that those students that aren't involved otherwise are actually the ones that end up being leaders in this type of environment. I had a student last year when I taught this who was an English language learner and was very inactive in most other classes. And he ended up being one of the most active students and most engaged students in my modeling classroom. And it's a really exciting way that we can engage students. But they're building a model in this picture here of a orbit of a comet. And they did this by using the modeling instruction techniques that you learn in the modeling instruction astronomy course, using data collected with one of those unistellar telescopes that I just mentioned on an actual comet, a current comet that was orbiting. In fact, I think it might have been that same comet that was recently in news that maybe I can't remember for sure. So don't hold me to that.
You on that? Yeah. Okay.
But they did something called photometry, which you'll get a little taste of today. And then they modeled the orbit of this comet. And and you won't necessarily be able to do this in your classroom, but because I worked with the scientist through my PhD, I was actually able to have that scientist, the comet scientist, zoom into my classroom and talk about this. And that was a really exciting thing to do. But you can always reach out to scientists at universities, and sometimes they'll
astronomers really love to talk to students. This is something that I didn't realize until I met Carl, is they are happy to take time to educate the public, and they're very pro citizen science. They want just plain folks looking at the sky, and if possible, you know, collecting data with them to help them find new things.
Yeah, a good bit
So
of
if
them.
you're near a university with an astronomer, it wouldn't hurt to ask them.
Mhm. And that's something we can help you with too. And we could talk about that at the end if there's time, if you have any questions on how you can
Yeah, we
connect
can
with
hook you up maybe.
Yeah, so I think that's a good overview, and there are more slides on here that I would like to show you at the end if we have time, especially talking about like more in depth, like what happens in the course, like what are some other exciting things? What's that Rubin Observatory project that we talked about? Because that's something that's really exciting that there's webinars in the future. But let's hold that until towards the end after we get through some of the activities that we have planned. So I'm going to stop my share. And then,
Okay.
Colin,
And
do you
we're
want
going to
to get
talk, so
started with the
please
next
feel
part?
free to open your mics because we're going to have a little discussion here to get things rolling. You know, all of us teach science, so I'm just going to assume we all do. And I think at some point in time, we all ask our students to collect data. How in the world do you collect data on where does astronomy data come from? We study stuff that's far, far away. How do we get data?
From the light?
From light. Okay. What else?
I'm going to put up a really cool picture that the James Webb Space Telescope took while we're having this discussion.
Okay. Sounds good.
I teach chemistry,
Uh-huh.
and we talk about how the images that you see here are showing a type of light.
Mm-hmm.
It depends on the type of elements that they're made of.
Okay.
So that would be my end here.
Okay. So light comes in. Not all light is created equal. What are those bits of light that we collect? What do we call those bits of light that we collect?
And electromagnetic radiation because of the temperature?
Okay. Okay. And the light is different because the differences in light have to do with the temperature. Okay.
Yes.
What else? So how would we collect these particles?
Telescopes?
Depends on what type of light you're talking about, whether you're talking about visible light or, I mean, you need sensors for all the different aspects of the spectrum.
Okay, so we need
Wavelength.
sensors to collect light, and we need different kinds of sensors to collect different kinds of light. Other thoughts? Other thoughts about how light is collected?
We have in the chat, Anna said observations over time.
Observations over time. What? How do we make those observations? Telescopes.
Johanna said wavelengths and oh yeah, and then
Okay, telescopes, wavelengths. Yeah. So the image on Dan's screen is an example of something that was obtained with a telescope. Is there data in that image?
I mean, yes.
Okay,
There's I mean, there's definitely data in that image. Just
okay.
depends on what kind of data you're talking about. There aren't necessarily quantitative data points. You need underlying stuff for that. But I mean, you can do counts of colors and sizes, or apparent brightnesses and things like
Okay.
that.
Okay. Okay. So images have data. Is that a fair statement?
I believe so.
Okay. All right. Is it time to do a breakout, Dan?
Yeah, I think so.
Okay.
It's like what do we want to do? Two rooms?
Yeah, I think 2 rooms is good. And I am not going to assign the co-hosts. And I'm going to create those rooms.
And I'll
Okay.
get the
All right. So
thing too. Should I get that?
what are you getting?
The whiteboard or the
Yeah, so put that, so Dan is going to put a Google slide deck into the chat. And that's going to be your whiteboard for your group to write or draw on. And we would like you, and he's going to also put the prompt in the breakout. We would like you to represent your model of an astronomical image. Where does an astronomical image come from? What is it made of? What is it made of? Any questions before I open the rooms? So you're just going to work together with your roommates, turn on your mics and talk with each other and draw or write. We would like to see multiple representations on your whiteboard, but show us what your conceptual model is of an astronomical image. And if possible, identify things that are measurable.
And you can, if you want to bring in pictures that you add, you can draw in the slides. So if you want to make shapes, arrows, add text, do whatever you want to, make the board yourself, a board your own for your group. Now I think there's 6 total slides in there, just because we weren't sure how many, people.
Yeah, just the first 2. Well, we may use 2 more slides as we go along in our webinar, but for now, just the first 2 slides. If you're in room 1, use slide 1. If you're in room 2, use slide 2. Questions?
Yeah, introduce yourself to each other once you get in there, and then think about the discussion we just had and a lot of the great examples that everyone had just shared, and then start adding stuff to your board. Colleen and I will come into each of the rooms in a few moments to check in and see if you have any questions. But start off by introducing to each other and talk about how you want to create a model of an astronomical image and what it's made out of.
All right, and how many minutes are we going to give him, Dan?
Let's start with 7 minutes and see where we're at, and if we
Okay,
we
and
need
we can always extend that.
Feels like if we need less or more, we can we'll adjust. So we'll be in the chat on you to see.
Yeah, as we visit rooms, we'll get an idea if more time is needed. All right, I'm opening the rooms, and they're back.
Welcome back, folks.
All right, so everybody's got something on their slide that's good. This is a starting point for conversation. This kind of small group brainstorming is typical of the way we introduce a concept in a modeling classroom, where you just get some ideas, with your small group, get your, collective ideas down on a whiteboard. And then you can imagine with a larger group, the more folks, the more ideas there are. And then we share our ideas, look together at the boards, and put together where we are, in terms of beginning to build our conceptual model.
And it's a great way too to start letting questions and things pop up from participant students, so trying to understand, well, what are we supposed to do? And like, what is this? And then, other students or participants or teachers can help loop people in. And then as you're walking around the classroom, especially in a real classroom, you'll get to kind of hear and see what's happening in different groups. And it's a really organic way of learning. It's just pretty special.
Yeah. and drop in and out of conversations. You can also, it's easier in a classroom to tell when people are ready to gather up and, have a whiteboard meeting and share their ideas. It's a little harder in Zoom with multiple breakout rooms to figure out when people are done talking with each other and ready to show what they've got. So
And
you
I've
want
gotten
to
better. I've gotten better at it, Colleen, about
Yep.
understanding how long it takes for people to do boards, but it still always takes longer than I expect.
Well, but sometimes, so this is just a classroom management strategy. Sometimes giving people a deadline and sticking to it and having them, forcing them back to the whole group before they're quite ready keeps them focused, and also makes them start sooner the next time they whiteboard, to get something on the whiteboard so they'd be sure to have something to share.
That's a good point, because I think, and I'm not as experienced educator or modeler as Colleen, and probably some people in the room here too. Is I think especially like younger educators, not as experienced educators, will be tempted to just add more time. Because I've definitely done that, where I'm like, oh, they all need more time, so I better give them more time. And maybe if the whole room is like that, maybe that's, maybe you didn't give them enough time, or maybe the instructions weren't clear enough or something. But I think it's important to try to do what you said too, Colleen, to not train them that they can always get more time, because then you're just, I guess.
Yeah, I think you have to, kind of set an expectation. And they're I think students are used to dealing with time limits and expectations, and they will rise to that. And it's okay, especially at this stage, to have a partially formed idea. So share your partially formed ideas, and everybody's ideas taken together make up a larger whole.
Nice. All right, should I go ahead and start sharing the boards?
Yeah, let's do it. Okay. Oh, look at the beautiful pictures. Where did
Oh, I
that
just
come
realized I was typing on the wrong board.
Oh
Sorry.
no, how funny.
That happens.
Okay, group one, want to talk about your board?
I mean, I guess
So-
I can, or
Okay.
if someone else wants to. We just were really starting with things out there in the universe that are emitting things across the electromagnetic spectrum. And then that's traveling across the universe until it's picked up by some sort of telescope sensor, depending on what you're collecting. And then that feeds into a computer where the information is processed and turned into a picture that's being displayed on the monitor. So it's kind of the process we put on there.
Okay.
Nice. I love the arrows that you put there. That was really nice, easy to follow, kind of
Yeah.
the thinking that you were going through in your room.
Yeah, and I especially love that picture at the top left. Where did you find that?
That is awesome picture, isn't it?
It is. Huh.
Sometimes I see these and I'm like, is that a real image, or is it art, or is it AI? I don't even know anymore sometimes.
I know. I know. I tell you. Well, I think it's a Hubble image, but that's just me being old school and thinking that only Hubble makes these most beautiful images. Okay. Okay.
Any
So
questions for this group? Anybody have any questions from the
group
other
two, you
group
want to
about
ask them questions?
So we had also talked about how you can see atmospheric compositions as well, and star wobble,
Oh, okay.
which is what I added on the second slide.
Okay, well, let's move along to the second slide and see what we have. Okay. Okay, we got pixels here. Okay, now we are drilling down to particles. Electric signal sent by stars made by a telescope needs light.
I love how these boards look so different with the same question. I enjoy that in class. And what you said about the time limit for high school students is critical.
Yeah, and it's I have found, actually I learned that from middle school modelers, that you don't want to give them lots of time. Because they will fill up the time that you give them. Sometimes with chit chat about what you did on Saturday night, and sometimes with other things. But my middle school modeler colleagues tend to run a really tight ship when it comes to the time allotted to students to create a whiteboard. Usually in the beginning of the school year, you give them more time because they just have to get oriented to each other and learn to work together and, like develop values around what constitutes a good whiteboard. But later in the year, man, it's bam, 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 bam. They get through it really quick. So, but you guys are doing great for first timers. Well done. 2 thumbs up. All right, let's continue looking at this board. Pixels. We're really talking about the pixels, and there's color there. And so we know that there's red, green, and blue light that make up the color information in a pixel. And color gives information about distance, temperature, chemical composition. See, there's a whole lot of, isn't there a lot of information encoded in an image? That's amazing. How do we get it out of there, Dan?
I don't know. That's a good question.
How do we get that information out of that image? Because we got to have data, right? We got to have data to draw conclusions.
Graphs, charts are a big help.
Charts. So, are we going to end up with numerical data?
Oh yeah, there's lots of numerical data in astronomy.
Okay, so where's the numerical data going to come from?
The observations in the different wavelengths that the telescopes make, the deep space observations.
Okay. Okay. So what do you think, Dan?
Yeah,
Good enough to go to the next step?
To the next step, yeah. So
Okay.
I just real quick though, I wanted to just show an image of my cat on my phone, just because cats are always fun, right? And he's being we caught him eating his sister cat's treats, so he's looking guilty.
Yeah, I see.
Sure, right? But
see.
if you have a smartphone, if you have an iPhone and you swipe up, there's like more information here.
Oh,
It
metadata.
even tells me it's a short hair cat. How does it know that? Right? It's so crazy what our phones know, right? But then it also tells you, about my camera and the different exposure settings, and oh geez, it even gives you, now you know where I live. It even tells you geographic information. How does it know all this stuff, right? And we think it's just a picture, but there's all this other stuff in there. You might have heard of metadata before. And we're going to get meta with our pictures, and try to understand what lies beneath them. So we have right now what we're going to do is I'm going to do a little demo. So this is in the full modeling course. We actually will show you how to do the things I'm about to show you. We'll take the time to be like, okay, you click on this and this.
You're going to do it. Right.
Yeah. But right now I'm just going to do it just because for the sake of time, there's a teaser, right? But in the full one, we actually teach how to do this. You have the breakout rooms to actually practice that and do activities associated with it. So I'm going to use this program,
which is free and it's online.
Yep, and we'll get you the links to all this stuff in the chat, before you leave, so you can play around with this, and we'll give you the data that I use too, so that if you want to try this on your own or just mess around with it later, you can. But first, we'll just show you this. So this is a web-based software called Astrolab. And this is based off of a program called JS9.
JS9.
Right? And what JS9 does is it brings astronomical images displayed to your browser and desktop. And it uses this thing called, it uses special types of files called FITS files. So a FITS file is a special type of image file. Is anybody a photographer here? Oh, okay. So Kathy, do you ever shoot in RAW?
Yes.
Yeah. So could you tell everyone what a RAW image is, and what, like, people that don't know photography, what am I talking about?
A raw image is that every pixel on the image gives you exactly what is measured. So it's not filtered, not made nicer. It's just really the raw data which are measured.
Yeah, and then if you, so my mom's a photographer, and I don't really practice, but I consider myself an amateur photographer myself, and I have some DSLR cameras, and I know what it means to shoot in RAW. And if you bring that RAW image into Photoshop, for example, as Kathy said, there's that raw information that's been, unprocessed, and it hasn't been diluted or compressed in a way, so you can really make the best image that you want. You get these beautiful images from a wedding or graduation or of nature or whatever it is that you want, right? So I kind of like to think of a FITS file. It's kind of a similar thing, but for astronomical images. So it has all the raw data and all the metadata that might exist in there that can help us understand what we're looking at to do science with it. Because in astronomy, we can't actually, at least not yet, we can't go to these nebulae and these galaxies. We can't visit there yet. We might not ever be able to do that. But we can use instruments to collect the light from them. And then very creatively, we can start to understand what's happening in those images by doing some pretty interesting analysis using image analysis programs like this program called JS9. So there is a program called JS9. It's web-based. As I said, you don't have to download anything on your computer. Most schools we find like don't have restrictions around using this in a browser for like Chromebooks and stuff. Occasionally, you might have to be like, unblock this site, because we know how annoying our IT people can be in blocking everything that they don't know about. But it's not as much as other sites. And again, you don't have to download anything. So another version is JS9 is called Astrolab. So this is basically the same program.
This is a slimmed down version.
Yeah, it's a slimmed down version, but also has some features that aren't in this JS9 right here. So this JS9 is an open source thing, meaning so you could get the source code from GitHub and you could create your own applet if you know how to do so. And this is something Colleen and I are scheming about, is trying to create our own best version for the astronomy modeling that we'll host through the modeling site at some point in the future. But this particular JS9 version, I'm gonna give you a little taste of some cool things that we can do. So I am gonna open up some image. Do you see the image folder that I opened, or is it just?
No, we can't see that. We're only seeing Astrolab Stellar.
Okay, good, because I don't want you to see that.
Okay, all right.
Yeah,
because it's secret. It's full of secrets. Got it.
Okay. All right. So now you see I've loaded some things, right?
All he did really was in his file, he clicked he checked 4 images and clicked a button that said open. And then it, bam, stuck those images right there on his screen. It's very slick.
Now these images, you would not be able to open these on your computer unless you had a special type of astronomical software like JS9. However, the computer-based one's called DS9, but it's the same thing. But you need a special type of software to open this. Just like you couldn't open a raw image unless you had a special type of software on your computer to do so. So
okay, they don't look like much though, Dan. I see just a couple of little dots there. Not
it's kind of
very
hard to
interesting.
see, right? It might just like
Yeah.
a bad image or something, right? But so there's some things that we can do to this, and there's something called scaling, and we learn more about this in the course. But basically, I can choose to amplify or de-amplify aspects of the image. But as I change
Ooh, look at
this,
that.
we can start to
Okay.
see more, right? And I don't want to go too much because then I can't see anything. But then if I go too little, I don't see anything. If you, again, if you have, if you've messed around with your images on your smartphone, or if you use Instagram or something, and you can go in and adjust the settings, you change the brightness and all that stuff.
Yeah.
Kind of
So
a
here's the
similar thing.
Goldilocks zone.
Yeah, you get your Goldilocks zone, and I can do this with each image. So let's go ahead and do this real quick, just so we can see things better. So I'm just
What is
adjusting
the
by
difference
eye.
be-
What's that?
What's the difference between the three images?
That's a good
That's a
question.
good question. We're
Something
going to see if we can figure it out. They all look a lot alike, don't they?
We're gonna try to figure that out, because they kind of look similar in some ways, right? Like,
do.
let's look at the first image and the second image. Like, it looks like the same star field, right? And then this third one, okay. What if I just scroll through these real quick? I'm just gonna keep clicking through these. And while I'm doing that,
Look
just
for
look at,
differences.
see if you see anything that's different when I click through them. And if you see
Move.
something, let us know.
The spots move.
Oh, spots move?
Yeah, where do you see that at? Could you describe where in the image you're seeing something move? Is it in the left, the right, the top, the middle? Like where at?
In the middle, there are two very clear spots, and they just move a little bit on my screen.
Okay.
Yeah.
Anybody else see that?
Yep.
Yes.
Yeah, I see it. I
Yeah.
definitely see it.
And I'll
Right
go ahead and point
that
out with my
guy?
mouse.
Yeah,
Do you see
that
where
guy.
I'm pointing with my mouse? You see my mouse on the screen, right?
Yes, we do.
Yes.
Okay. So that if you look in this area, if you didn't see it yet, kind of in the center, and I'll go ahead and click through the images again, you should start to see something move. Oops, hold on a second. Push the wrong button.
More stars are visible. Or whatever that is. It may not be
Yeah,
stars.
and I think you might see some more stars in some of them because I might have adjusted the brightness more on others than others. But the main thing that we want to point out that some of you've seen is there is this object moving. What do we think that is?
Could be a satellite,
Asteroid.
Asteroid.
comet.
Asteroid.
Yeah.
What do you think your students are going to say that is?
The
An
stars
alien
move.
spaceship.
I've gotten that a lot. It's a spaceship. It's a UFO.
It's a UFO.
Yeah, so but it's something moving, right? And then we'd have a conversation about this. Maybe we'd put them back in their groups with this activity, and they would discuss what they think it is, and we'd share that out, and then get them to open these files and go from there. So I'm gonna switch gears a little bit, and we'll talk more about this as we move on. And I want to show you another thing that we can do with an image in JS9. And I'm gonna go ahead and close out these other two for now.
So Dan, these are obviously pictures of the same star field. But
Yep, they're all the same. Mm-hmm.
But they weren't taken at the same time. Am I making a correct assumption?
Yeah, and in fact, I'm glad you asked that. So what I should probably do, and I'm gonna open these again because I closed them out, but you brought up something that I think is important to show. So let me just make these brighter again real quick. And I want to show something else that I hope this version of JS9 does this. If it doesn't, then I'll open it in the other one. Okay, it does. All right, so
yeah, it's the Fitz header. Yeah,
there's this thing called a Fitz header, and I have this first image selected. And if I open this, do you see the window that pops up that says details of observation?
Yeah.
Okay. This doesn't really show us.
Doesn't give us the time though, does it?
Yeah, let me try opening it in the other version of JS9. So let me do that over here real quick. Let's open one of these.
We used to, while Dan is opening these, we used to have a version of JS9 that we could use that was installed on a Berkeley computer that did everything in the same program. And we only just found out on Thursday that that Berkeley website isn't operating right now. And so we're making do with two different, what the heck?
So I think maybe this particular image just doesn't have the information.
Doesn't have much metadata.
Let me open up a different one just to give you an idea of what we're
Show you a real FITS header. Because there is a ton of information, metadata that is attached to every photograph that you take. That, among other things, tells you the exact instant that the photo was taken.
Yeah, so this image that I just opened, this actually comes from one of those unistellar telescopes. So this is from one of those little citizen science telescopes that I talked to you about. And oh wait, maybe I have the wrong image selected. No,
they're giving really truncated data.
Okay, well, I'm not going to spend any more time with trying to get the FITS header to show what I want to show you. What we'll do is we'll move on, and then when we're doing something else, I'll get an example that works. But basically, what we wanted to show you is that just like on my phone, whenever I was showing you the picture of my cat Queso, there was all this metadata, this information about like where the picture was taken, the exposure of the camera, stuff like that. So in a traditional FITS header, they would show you that kind of information. So it would show you like the exposure of the camera, the coordinates of the object in the sky, and other information that could help us to understand what kind of data might be within the image itself. So what I do want to do is show you the next tool that we can use to try to understand what's in an image. And to do this, I'm gonna zoom in to one of these stars, one of these objects. I think it's a star. And I'm gonna go and use this tool called measure brightness. Wait, look, there's other tools here. We're not gonna have time to look at these other tools, but there's measure size, and there's other tools and other versions of JS9 we can use too. And after I click on measure brightness, I get this window that pops up. I can add this little measure tool, okay? And I can resize it. And what I'm gonna do is I'm gonna zoom in. I'm gonna zoom in even more. And I can actually change some of the ring sizes here. And what this is called photometry. So photo,
light,
measuring light. So we're measuring light. And this is actually telling me something about the light around in that circle that I drew.
Check it out, numerical data. We love numerical data. We can make graphs with numerical data.
Yeah, so there is quantitative information we can pull from these images. And I could go and I could add another target. And maybe I want to compare these stars for whatever reason. I don't know why, but maybe that's something I want to do for whatever it is that I'm trying to study or understand, or I'm just exploring to see what I find out. Oh, and hey, look, now I have two targets. Two sets.
Make your counts in the second target.
Yeah, and we could see like this one's much brighter. It's got a lot larger counts, and this one's got a smaller number of counts. And a really cool thing that I like about this Astrolab calling that I realized.
Yeah, you download. Yeah.
You can download these results as an Excel spreadsheet and then put those into Google Docs or Google Sheets or whatever and do stuff with that. Much easier than JS9. So JS9 is great, but the one as we said is the best one we can't access right now, which we're fixing. And then this one doesn't have the stuff we want. This one does have the stuff we want, but not all the stuff we want. So it's a goal of ours to create a version of JS9 at some point, hopefully in the near future, that has all the stuff we want and more and is easier accessible. But that's something that's in process.
Right.
So I think what I'll do is I'll stop there, because I just
Okay.
want to do a little show and tell of
Yes.
some tools that we can use, some things that we can do with an image using a special type of software. And then maybe what we can do now is have you head back into your breakout rooms and see if maybe you could, I don't know, refine your model a little bit, add to it, add new ideas. Did this make you think of anything? Does it bring up new questions that, maybe you're more confused? Then
Right.
that's great. Just detail whatever you're feeling, whatever comes up after that. And then
Right. So this is a model so far, right? We started out with an idea of what was in images, and now we have a more fully formed, more refined idea. So back to our breakout rooms for what, 5 minutes?
Yeah, let's do 5 minutes. And real quick, there was a question in the chat from Anna asking, are target counts observations? I'd like you to think about that a little bit and talk to your group about it. But what I will say is that these target counts come from the same observation. So just real quick, I will share my screen again just to show you these target counts from these two stars, these two objects, come from the same picture. So I came from the same picture from the same telescope. This is one picture from one telescope that I got two different target counts for two different targets within the same image. And then, I'm going to do one more thing. I lied. I want to try to zoom in even more. And I just want to ask the question real quick. As I zoom in even more. What is that? So weird that when I zoom in, what does it look like? And there was some things that were said earlier in some of the breakout rooms about what that might be called. And maybe that's something to think about, is like, when I zoom in, what am I seeing when I zoom in all the way? Or when I zoom out all the way? Very interesting that the image is made up of something. So think about that. And then let's have you go back to the drawing board.
All right, add to your boards whatever you can, 5 minutes, and we're going to come back and share again. I'm opening the rooms. Okay, we're back.
All right, let's share these boards. Okay, someone from group one want to tell us anything new that you added? Any new thoughts that came up?
We added that there's a lot of metadata or fit data if you're talking about astronomical images. We believe that pixel counts is equal to target counts. We didn't Google it. We said, on your honor, don't Google.
Okay, all right, good for
We
you.
know the time the image was taken, and we can observe movement of comets and asteroids through observation and use the image data to create graphs, tables, and charts.
Mm-hmm. In fact, with that comet, if you know how far apart those images were taken, you can begin to think about how fast the comet is moving.
Yes.
Interesting.
Nice. All right, how about group two? Can you tell us anything new that you added?
We were talking about the circle around the center pixel, what you showed just a few minutes ago. And what does it mean? Is it an artifact, difference in signal strength, rotation of the star, Doppler effect, movement of layers of the air between the telescope and the sky, moving of the Earth, measurement device, because also that can make tremble.
Yeah, what great questions. Great questions.
Yeah, those are really good questions. Okay, so where do we go from here, Colin? What do you think would be the next good step?
Well, I think you maybe, just to keep from frustrating people, you should answer a couple of these questions.
Sure.
Like, what about those circles? But then we should talk about what you can do with data, or what students can do with data, and maybe even what students have done with data.
Of course. Yeah. So first off, have we heard of photons before? What's a photon?
Light particle?
It's a light particle.
Particle.
All right.
And what do what do they carry with them? Photons carry anything?
Energy.
They have energy.
Yeah. Yeah, that's interesting.
Absolutely do. They're
Um,
little packets of energy.
yeah, so what we can think of when we look at these images, get my screen to be shared again here. And when we zoom in to an image, you can see all the different pixels. That's what those little squares are. And I found when I do this with students, most of them know what a pixel is, and they've heard of this before. So that's it's nice that they can understand what a pixel is and have some intuition about it. But why are some of them brighter than others? And these are the kind of questions that we'd ask. This has to do, with basically the detector and the
Right.
the
How the
photons.
camera works.
Yeah. So in the modeling workshop, we go through a series of activities where we try to understand astronomical image sensors and how they work, and further refining that model. But the question that came up is like target counts. What are those? These are basically the counts of, basically you could think of them as photons, like how many photons
Hit
per,
that little piece of detector.
yeah, how many photons hit that detector over a certain amount of time, right? And you can think about these little pixels as buckets. And this is a great analogy in astronomy is our telescopes collect light, and telescopes can be thought of as a bucket, and the light can be thought of as raindrops and water, right? And the more rain you collect in the bucket, the brighter that pixel is going to be. All right, so you can think of each of these little pixels as a bucket, and the ones that are super bright, they're overflowing with water, overflowing with photons, and that can tell us some interesting things, especially when we compare things. So what can we find out though? I'm going to go back to these slides, and I want to show you. Actually, you know what? I think would be a cool thing to show real quick. Let me pull this up real quick.
And
Okay.
while he's doing that, I'm just going to say what that target does is basically draw a ring around the place you want to count pixels in. So let's count the photons inside this center ring. And so the count that it gives you is how many photons struck the detector during the time that detector was exposed, because the exposure times differ. Maybe you're going to expose it for a minute. Maybe you're going to expose it for 10 seconds. Maybe you're going to expose it for 10 minutes. You can set that on telescopes, the exposure time. And during that time, how many pixels were collected in those pixel buckets within that circle. And then the outer rings are comparison rings, because you have dark sky outside your star, and but sometimes there's noise in that sky. There's extraneous light, and you want to subtract out you're looking at it through a foggy sky, so you want to subtract out the scattered light so that you get just the light that was coming from that star. And so the concentric circles do that. or allow the program to do that.
Thanks, Colleen. And there's some more advanced options where you can get more information, like how many counts, like, you know, per second per exposure, like, come through. And I can't remember how to do that in Astrolab, but there's there's some good videos, and we'll you know, before you leave, we'll add a bunch of links to the chat that you can save that can help you to explore this even more.
Right.
But
Okay.
I wanted to just share real quick this cool event that I did with the SETI Institute with the Chabot Space and Science Center in Oakland, California. So this is where I'm in here somewhere. Here I am right here with 16 high school students, and this is my colleague Ian Weaver. He's an astronomer at the SETI Institute, and we used these telescopes. In fact, here's a great picture of the telescopes.
That's
right
a nice
here.
one.
Right. So we set up all these telescopes for an overnight observation to collect data on a star. And that data looked, you know, much like one of these images, right? Just a star field. But we did photometry on a very important star that we wanted to look at. And we had a lot of fun. We watched movies, we listened to music, we had performances, we collected data, we stayed up until 5 or 6 in the morning. We did cool art with photography and stuff. But that data that they collected was then used in a paper. This is with the Astronomical Journal. It's a peer-reviewed astronomy journal. And it helped with the confirmation and characterization of a new exoplanet and published astrophysics journal work. And let's see, I'm going to show you the
Check
figure.
out those light curves.
Yeah, I'm going to get the light curve up here. Yeah, so here's one of the light curves
Nice.
from their observation. So this data includes the high school students, but also other citizen scientists around the world. And what we see in this light curve is, well, we see a curve. And why is there a curve? Well, we're measuring the flux, which is brightness, over time. Okay. And what we find is when we have an exoplanet that transits its star, that means the planet, from our perspective, goes in front of the star and then leaves the disk of the star over time. And when that happens, the brightness of the star actually goes down and then back up again. And that's when we can create this, what we call a transit light curve. So students actually got to contribute data that was used in this paper, and they are co-authors. So you can see in the co-author list, we have all of these high schools of students, co-authors on major papers. Now, this is the penultimum, you know, amazing, like, you know, the cream of the crop type of like example that can happen with this. But, you know, you don't have to be published in a paper, but students can do this. We give you data. You don't have to have a unistellar telescope. We can give you the raw data, and they'll create light curves, or they can.
Or they can subscribe to telescope. There are robotic telescopes around the world that students can get a subscription to download to get the telescope to take pictures and then download that data and analyze it. Kids as young as middle school have captured exoplanet transits. This is not rocket science. Well, I don't know, maybe, but they can do it.
Interesting. They can even use data of rockets in space. So one of the coolest examples is tracking spacecraft in space. So we don't have anything in the modeling curriculum yet for this, but it's something I'd like to add at some point in the future, Colleen, is data when we're tracking new space missions. So like we can track an asteroid through our solar system, we can also track a spacecraft like the James Webb Space Telescope. Or you might remember, so those of you that follow space news, we crashed a spacecraft into an asteroid recently called the DART mission. See if we could redirect the orbit of an asteroid so it wouldn't impact Earth and kill us all one day by crashing a spacecraft into it. We can observe these with these small telescopes. We can collect the data. We can do photometry on them, and we can make different representations of the model of that, like graphs and et cetera, to understand things about this. So these are some of the things that we can do that are very exciting. And this is an example of the astronomy modeling curriculum. We have 4 units. The first one is how do we map and measure space around Earth to get our coordinate systems, right? How we get distances and measurements, how do objects interact in space. So we're talking about motion and forces, something called Kepler's laws, light. So we really get into photometry and creating like light curves. And then the evolution of the universe, cosmology, and this idea of the search for extraterrestrial intelligence. These are the 4 units in the modeling workshop. And this is just another example of a board where we're modeling the orbit of objects in our solar system. I would like to just real briefly, and then we'll start to conclude, just mention what the Rubin Observatory is, and encourage you to check out the webinar we have in December. It's also free to join, which is with the Rubin Observatory team. So the Rubin Observatory is a brand new telescope that has been in development for 20 years, and it's finally almost done. $1.5 billion has been invested by the National Science Foundation and the Department of Energy for this single observatory and the project that it's going to do called the Legacy Survey of Space and Time. And it's got the largest camera in the world, the Guinness Book World Records holder of the largest camera. It's 3.2 gigapixels of the largest camera, as big as like a VW car. And it's going to take a picture of the entire southern sky every 3 days. And it's going to do this for 10 years. So every 3 to 4 days, it's going to get a picture of the entire sky. It's going to create 10 million new alerts every night, 20 terabytes of data every day. And over the course of 10 years, 60 petabytes of data. This is an insane amount of data. It's a huge astronomical project, and it's going to create so much data that the astronomical community cannot keep up with it. So there's going to be a lot of citizen science opportunities. And with data and modeling instruction, we have a great opportunity to have engaging activities in our classrooms. So that's why we've teamed up with Rubin Observatory for some webinars where we're talking about how you can use modeling instruction and the already really cool education activities that Rubin Observatory has in order to engage each other on current astronomy that's happening. So I think I'll stop there, and then let's start to wrap things up and start to share some of these links and stuff too.
So I'm putting some links in the chat right now. Since time is short, I gave a link to the Schools Observatory How to Do Photometry site, the registration link for our Modeling Astronomy with Exoplanets course, which is going to be this spring starting in January. It's a 3-credit 45-hour course, meets once a week for 3 hours. I forget the day of the week that it meets, but that's a very cool course. It fills up, so you know, consider it. The people that have taken it really love it. And some of them thematize their physics class, make it a physics in the context of astronomy class, because this really an astrophysics course. And some teach freestanding, you know, semester-long or year-long astronomy courses using this. And then there's also a link there to register for the Rubin webinar. The Vera Rubin webinar that's in December. And last but not least, we would love it if you would take about 1.5 minutes to complete this really short survey to let us know how we're doing, you know, and if you think there's something we could do better. But we really appreciate you coming today, giving up a little bit of your Saturday for this. Should we put our email addresses in the chat in case somebody wants to reach out with a question, Dan?
Yeah, sure. I'm going to put my SETI one in. And then if you want to put whatever email you prefer, Colleen.
Yeah, I always use the same one, Colleen@modelinginstruction.org. So if you have questions, we realize this was really fast. We could have filled up another hour probably with stuff. We had a whole image colorizing where we would have layered red, green, and blue images to give you to let you make a color image, and we just didn't have enough time. But it would have looked like that. Would have been very cool. As usual, we planned more than we could possibly do. But we're really delighted that you came.
Yeah, and we hope to see you in future ones. Please come to the Rubin webinar and or consider joining the full astronomy modeling workshop in January. And thank you again for coming. I also included a link to a folder for the FITS files that I used for the asteroid demo that I did. If you're welcome to download those and try opening them in Astrolab and trying to do the same thing I did if you'd like.
Yeah, did we give them the link to the version of JS9?
I don't know, but I will put that in into the
To the chat as well, the Schools Observatory one. Yeah.
yeah. So here's the
Yeah.
software link, the School Observatory.
Yeah. So, snag one of those images and try it yourself. Download the images and then upload them from your computer and see how quick and easy it is. You can also load files from, I think, from like a Google Drive file, maybe, or Google Drive folder. You don't have to download them from or upload them from your computer. So it makes it pretty easy to use in a classroom. We used to have a piece of software the students would use that had to be installed on their computer. Teachers ran into an issue with their technology departments not wanting to install software on student computers. So this web browser version is pretty bulletproof.
I'm having trouble copying from the chat. Is there?
You can save the chat. There's a little icon at the bottom of the chat. Or is it at the top of the chat that lets you save the chat? But Anna, if you can't, email me and I will send you a copy of my saved chat.
Yeah, and if you're on a computer, I'm not sure how it will be on a phone, but if you're on a computer, when you click on the button for the chat and you see that there should be like 3 little dots, maybe.
Oh, it's up there in the 3
corner.
dots.
I see 3 dots.
Yeah, and
So
if you
click on the 3 dots
and then click Save Chat, that will save it. Now you might have to hunt around your hard drive to find where it's saved, depending on your computer, but that will save to your computer.
Yeah, usually saves in a folder called Zoom.
Yeah, that's what it does for me too.
Yeah. Cool.
Are there already activities on the AMTA website which we can download?
There are a lot. Well, wait.
About
There's the
astrophysics?
astronomy curriculum. I don't actually, I think maybe the astronomy curriculum is not all on the website because it is chock full of image files. And it's like too big to put on the AMTA website, but it is in Google Drive. And if you contact one of us, we can get you a link to it. You're assuming you're a member of AMTA. Yes, Kathy?
Yes, I am.
Okay. So then, yes, we can get you a link to it.
Okay, thank you.
Sure.
Mm-hmm.
Yeah, there's a full curriculum that has been used for a full year astronomy course and has also been used for a 1 semester astronomy course. It's too much for 1 semester. I think it probably needs to be supplemented a little to make a whole year course, but there's a lot of stuff there and more being added all the time.
So can you tell more about the format of the actual course for the educators?
The course that begins in January meets once a week. It meets from 4 p.m. to 7 p.m. Pacific time, 7 to 10 Eastern time. I don't know what time zone you are in, but the idea is that teachers from across the country can take it, and everybody's out of school at that at that point in time, but probably not in bed yet by the time the class ends. I'm afraid for someone in the Netherlands, this would be in the middle of the night for you. Although I will tell you that
Had people do that.
we did have one student that was teaching in Saudi Arabia who came to class, and it was something like from 2 a.m. to 5 a.m. for him.
He didn't make all the classes, but he came to
He
one,
wanted it
a good bit
bad.
of them.
He really wanted it bad. So you know, it's doable, but I don't remember whether it's meeting on Tuesdays or Wednesdays this coming year. Maybe Sue knows.
Yeah. Well, it's in the link I think that we sent.
It is in
right?
the link, the registration link for the course, but so 3 hours once a week. It's a 3-credit course.
Wednesdays.
Credits are optional. You don't have to pay for credits, but they're very inexpensive at $79 per graduate credit. Where are you ever going to find a deal like that somewhere else?
You have to send in your bachelor degree or your master degrees, which you have had here in the Netherlands, because I have tried to do another course of modeling instruction, and I
Yeah.
have to have my whole diplomas to be translated, which costs a lot amount of money.
Huh.
Hmm.
Huh. Okay. So I'm not sure how that works in, you know, in other countries. But in the US, for a graduate, you know, graduate credits can be accepted for a master's degree program if the university, you know, they ask you for a copy of the syllabus, and they look for it to align with some program that they have. Every master's degree program has their required courses that you have to take, and then they usually have some optional classes. And this class fits into an elective that someone might be able to take for credit as a part of a master's degree in most US universities.
Okay, it means I have to translate everything. Yeah.
Yeah, I apologize. We don't have a relationship with the European University to be able to do this. Maybe someday we can figure that out.
No problem.
So
So you know too, as far as like the structure goes of each night, it's kind of similar to what we did today, but you know more involved, where you know there'll be you know some sort of phenomenon that we show you, and then we put you into breakout rooms and you play student mode, where you try to think kind of like your students. But you're also students, because most of the people that are taking the course are learning, right? So you are in this mode where you're learning as a student would, but as a real student yourself too, and you're learning how to use these tools, and you're using a you know online whiteboard, such as like the slideshows we did to develop your models, and we go through all 4 of the units for all kinds of different activities, where you know you're not just listening to us talk to you, you're actually engaged as you would in a
right.
modeling class to do things in real time. But then we'll also do tutorials, you know, where we show you how to do things in real time as well. So it's a good mix of being engaged and actually participating in an activity, as well as getting some instruction as well.
And you know, all of the physics ideas that are part of especially Unit 2, which is forces in motion, really, you know, and fields, are done via image analysis, like astronomers do. Astronomers can't go out with their tape measure and take measurements. They have to get their information from images, and so all activities are done via image analysis.
Actually, you know what? There is a new one that we developed though, calling measuring the shadows from the sun.
Oh, you're right. You're right.
There are some new activities that we've developed, and hopefully more in the future will develop, where we can actually take students outside during the school day and do some measurement of data that can be used in a modeling class. So there's a famous experiment that is only a few thousand
Eratosthenes.
years old. It's only a few thousand years old, by Eratosthenes, where you just take a stick in the ground and you measure its shadow, and then you can find out the size of the Earth. And we have students do that in a modeling classroom. as well.
Yeah. All right. Any other questions, comments, concerns?
I'm sorry, I am going to have to ask you to email that because my 3 dots don't,
Your
they
3
just say
dots isn't
edit,
giving you a
delete
save? Okay.
for
That's
the,
fine. Just
for the chat.
email Colleen or I. Can you get our email address from the chat, or do you?
I can't copy anything from the chat. It won't allow me
Okay.
to.
All right. Let me, I will get your email address from Sue and,
I can put my email address in the chat.
oh, do that. That would help.
I'm sorry.
That's
It's
okay.
just not a,
No apology necessary.
Yeah, we don't mind sharing the chat with you at all, so no worries at all.
All right. Yeah.
I
Oh,
have one last question.
yes.
Um, a, a grant was alluded to get a telescope. Do you have any specific grant information about grants for telescopes? Our high school doesn't have one, and frankly, there's no budget for one.
Yeah, so we were talking more like large scale grants, and hundreds of thousands or millions of dollars to run like national or international education programs. That's what we were kind of discussing at the beginning. There are some smaller grants that do exist that could help you get a telescope. I don't, if you can hang on a minute, I might be able to find the name of it.
Okay.
And while Dan's looking for that, I will tell you that modeling teachers in the past have been successful getting small grants from local Rotary clubs
Oh,
or
yeah, okay, Rotary.
Elks clubs or Knights of Columbus or, whatever your local service organizations, Seroptimist International, which is a women's group of business people. Local service organizations have a budget. Every year they plan to give X dollars for education, but they often have no ideas about how to do it. And so people have been successful in getting small grants from organizations like that.
So what would be the average amount that you would want to spend on a telescope to get a quality?
Well, I'm going to let Dan answer that.
Sorry for I was trying to find
For the
right.
Unistellar. For the Unistellar, so the great thing about a Unistellar telescope is that it takes pictures and it's designed to take a series of photos. It locks onto something. It's you steer it with your phone. It's not hard to operate. And so you can aim it and point it with your phone, and then it just tracks that object. So it can take a whole series of photos, long exposure photos of something very faint. So it can see things you can't see with your eyes. And it makes amazing photographs of faint objects.
And that was the question was it
How much? How much do they cost these days? I don't remember.
No. So
like in the neighborhood of 3,000, something like that.
yeah, well, it depends on what telescope you get, but from the Unistellar telescopes, they range from, I think, minimum like $2,000 for a telescope up to more advanced versions up to like close to $5,000 for a telescope. There are lower cost digital smart telescopes out there. I obviously I'm biased because I've worked with Unistellar, but I wouldn't recommend them for the following reasons. They're not as high quality, number one. And number two, the Unistellar telescopes are the only telescopes in the world that of this type of telescope, the digital smart telescopes that's automated, that has a computer and digital camera on it that collects data, that's also connected with scientists that curate the citizen science. So with Unistellar, there's a MOU with the SETI Institute and Unistellar, where there's a small team of scientists, which I was a part of and still work with on an unofficial level now, that curate scientific targets for the network. And once you get one of those telescopes, you're given access to this online Slack community where you can talk to them and other citizen scientists around the world and other educators, and do your own citizen science observations with their help and support. And they'll give you your data and process the data for you. There's
wow.
no other digital smart telescope in the world that does that. And so you get a quality telescope and you get access to this community and this network, and they'll tell you about targets like the exoplanet that I had in my paper, where students were able to collect data and be co-authors. They always have new observations where they're trying to publish more papers. And if you're active on there, you and your students, if you collect data for one of those initiatives on that Slack thing, you could also be co-authors with your students in an upcoming publication, if that data is used.
Yeah.
Hmm.
Yeah. It's a
And-
really great citizen science community.
And you purchased the telescope from the manufacturer's website?
Yes, and that's just Unistellar. You can go to
Yes.
unistellar.com and find them. There is a grant with Toshiba that they offer every year, like between $2,000 and $5,000 you can use for STEM. I put the link of that in the chat, so we'll make sure we share that with you too. And I know there's at least one other small grant out there that I saw. I can't remember where it came from. I tried to look through my emails. I couldn't find it, but
The other one I thought of was Society of Women Engineers.
Oh, yes.
They have been good about giving grants in my area. I live in Sacramento. I'm not sure where you are, Anna.
North Carolina.
Ah, okay. But there are plenty of women engineers there too.
There are indeed.
Cool. Any other questions we can answer?
This has been great. Thank you.
All right. Well, thanks for dropping by.
yeah, thank you for coming by.
Thanks so much.
Yep, have a
All
great day,
right.
everybody.
Okay.
So, see you December.
Yep, see ya.
Okay. Cool.
See you then.